Okay, guys, so let's just quickly go through another module 3 question on transition elements, right? So the more practice you get with transition elements, I think the more comfortable you'll be going into the exam. So let's look at this question. And the first part is where they're asking us to just define the term transition element. So what is a transition element exactly? So when we speak of a transition element, it has to be a D block element, right? And it has to be one which forms one or more stable ions with an incomplete D electron subshell, right? So that D orbital cannot be completely filled, otherwise it wouldn't be a transition element, right? It has to be in the D block and it has to form one or more stable ions, right? So that's how we would define our transition element. And then moving on to part B now, they're asking us about cisplatin, which is a drug used in cancer treatment, and they give you the formula. Of course, they have their square brackets, right, which indicate that it's a complex ion of some sort, right? And in this complex ion, our metal or complex metal ion is platinum, right? And then we have 2 ammonia ligands in it, and we have 2 chloride ligands in it, okay? So solely based off of this information, they're asking us to deduce the oxidation number of the platinum atom, right? And so to do that, when you look at this square bracket, right? If there's no number outside of it, then you can just assume that the overall charge, right, on the complex ion is 0. And so if we do that, let me just get a pencil. So if we assume that the overall charge on it is 0, then we know that all the oxidation numbers inside of it have to add up to 0. So we know that ammonia doesn't have any charge on it, so that's 0, right? And we know that the chloride ion has a -1 charge on it, right? And there are 2 of them. So inside of these square brackets, we have a -2 charge, and we have 0 charge from here, so that's 0. So 0 plus -2 plus our unknown oxidation number, which is the oxidation number of platinum, would be X, right? So in order for the overall charge on this ion to be 0, then we know that X has to be +2. So that's how we knew that X, aka the oxidation number of the platinum atom, would be +2. So that's how we got +2 here, right? Because everything has to add up to 0. So this is +2, and we're moving right along. Next, they're asking us to suggest the shape of the cisplatin molecule, right? So they want to suggest a shape of this molecule. So what I did, right, I did a quick sketch just to kind of get a picture as to how everything looks. We know that there are 4 ligands in all, right? There are 2 from ammonia and 2 from chlorine. So there are 4 ligands in all. And so see how they're like around it, right? They're surrounding that PT2 plus atom. And so we see that there are 1, 2, 3, 4. So there are 4 coordinate bonds, 1, 2, 3, 4. And when we have 4 coordinate bonds, we know that we're gonna have a square planar shape. We can either have a square planar or tetrahedral, but in this particular case, it's a square planar, and the square planar is more common. So you kind of see here, it's like a square in a plane, right? So this is a square planar structure where we have 2 ammonia ligands and 2 chloride ligands, so 4 ligands in all, and we have 4 coordinate bonds, okay? So that's how we knew it would be square planar. We could just tell based on the formula here. Okay, so let's scroll down. Let me clear that working out and scroll down. All right, so now we're at part C, and we're looking at part I. It says to complete the diagrams below by inserting arrows to show the electronic configuration of each ion, right? So first one is Fe2+. So it's iron that has lost 2 electrons, and those 2 electrons were lost from the, where were those lost from? Those were lost from the 4s, right? So that's how we ended up with this for our electronic structure of the Fe2+ ion, where iron has lost 2 electrons, right? And then next, we're asked to write it for the Mn2 plus, right? So that's where manganese has lost 2 electrons. And so in the case of manganese as well, manganese had lost the 2 electrons from the 4s shell as well, 4s orbital as well. So this is what we end up with in that case, right? So next, they're asking us to use the information in C part I, part B, right? To explain why is it that Mn2 plus ions resist oxidation to Mn3 plus ions. So in a nutshell, what they're saying is that we will most likely see Mn2 plus. This is more common, right? And if you have Mn2 plus ions, it's gonna be hard to then oxidize it further to Mn3 plus. So it's gonna be hard to take away any other electrons from it, right? And so they're asking why, like why is it hard to get to Mn3 plus? And that's because if we look at the electronic configuration that they have us draw up here, right, we see that there's like all the d orbitals are partially filled. So all of them, they just have one spin up, right? One spin up electron in each of the d orbitals. If we were to go to Mn3 plus, we would have to remove one of these, right? And that would leave us with a completely empty d orbital, a d orbital that's completely empty. And that's not stable for the molecule or for the ion, right? That wouldn't be a stable ion. That's energetically unfavorable. So it's easier to have us to be in a state, or it's more favorable to remain in a state where you have one electron in each of the d orbitals than have one where there's nothing in it, right? So it would rather stay in this Mn2 plus state where all the electrons are distributed across all the d orbitals, all 5 of them, right? So that's in a nutshell what we're saying down here. We're saying that in the Mn2 plus state, there's extra stability that's associated with all the d orbitals being half filled, right? So 1 electron in each of them. And then for the Mn3 plus to be formed, 1 electron from one of these d orbitals would have to be removed, which would make for an unstable ion being formed, and this is unfavorable, right? So by that same token, we can extend this a little bit further just so you guys learn this concept of stability of these transition metal ions, is that if we look at Fe2 plus, Fe2 plus has what? Fe2 plus has 2 in this d orbital, and then all the other ones have 1, right? So it's easy to form Fe3 plus because it wants to have all of them only having 1 in each d orbital, right? So you can form Fe3 plus fairly readily because the stable state is when they're all partially filled and not anyone being doubled up like we have here for Fe2 plus, right? So that's how you'd answer a question like that. If it came asking you then on the converse, why is it easy to form Fe3 plus? It would be because if we form Fe3 plus, we would remove one of these extra ones, and we would just be in a state now where we have 1 in each, and that's more stable, okay? If that's not clear, definitely drop a comment and let me know. But just make sure that you have a good grasp of that concept, because this could very well be something that you're tested on, okay? All right. So moving right along to the next page, they're showing us a sequence of reactions involving compounds of cobalt with ions or complex ions labeled A, B, C, and D. And they're showing this is here, right? So we have A, that's cobalt, that's complex with the hydroxide ligand. Then we have water, so we have a ligand exchange reaction, and we're exchanging out the hydroxide ligand for the water ligand. And then that's B. Then we have ammonia coming in, and we're going to exchange the water ligand for ammonia. And then we have the chloride ion coming in, and we're going to exchange the ammonia ligand for chlorine, right? So this is your typical ligand exchange setup that you will see in transition metal questions or transition complex questions, right? Complex ion questions. So they're asking us to list the color of the following ions. Of ion B, we're starting with. They gave us for A that this one was blue, right? When we have the ligand exchange and we have the cobalt and the water being complex together, so that's hexaqua cobalt, right? in this case, we would see a pink color. So we put pink here. This is pink. And then here we would have, let me just be writing them down underneath just to help you guys see it and remember it. So the water, hexaqua cobalt is going to be pink, right? And then when the ammonia comes in now, that's C, what this is going to be yellow, right? So make sure you remember that. When we have the hexamine cobalt, that's going to be yellow. And then now when we have the chloride ion come in and exchange out that ammonia, those 6 amines, we're going to end up with a blue color, right? So this is blue, right? So that's just what I wrote here. B is pink, C is yellow, and then D where there's chloride ions is going to be blue. So just make sure that you have a good handle on that, as well as the one for copper, right? And be sure to always look, what element are they asking about? Is it copper or is it cobalt, right? Make sure you don't get confused on those because they have different colors, right? So make sure you're clear as to what metal they're asking about. And in this case, they're asking about cobalt, okay? All right. So then moving right along, they're asking now to sketch the arrangement of bonds in the ion labeled C, right? So this ion is what they're asking us about. And this ion labeled C is where we have what? This is the hexamine cobalt, right? Complex ion. So we have 6 amines or 6 ammonia ligands surrounding that cobalt. So that's what I drew here, right? So that's what I drew here. So I have my cobalt ion. I know it's 2+ because again, the overall charge outside of the square brackets, it's 2+. So I know that the cobalt, the ion, the transition metal ion of cobalt is 2+. And I know that there are 6 ammonias around it. So I just kind of drew the 6, right? So I have 1 here, 1 here, 1 coming from here, 1 coming from here, and then 1 coming from this side and 1 from this side. And I just kind of sketched out this shape, right? The general shape that would have. So they just asked us to sketch the arrangement. So that's what I did. If they asked us about the shape, guys, what shape it forms, it would be an octahedral shape because there are 6 coordinate bonds. So I'm just going to write that here just to enhance your learning, right? So there are 6 coordinate bonds, right? Because I drew 6, there are 6 ammonia around it. So there are 6 coordinate bonds, coordinate bonds. And so as a result of that, this would be what, an octahedral shape, right? So if that could have been a question as well, what shape is that? Once you've sketched it, tell me what shape it is. Well, there are 6 coordinate bonds, 1, 2, 3, 4, 5, 6. So it's an octahedral shape, okay? So that's just an extension of the question, just so you guys can learn as we go along. All right, so let me clear that. All right, so moving right along for part E and final part of this question is they're asking us to state the changes that would be observed when a solution of copper-2 ions, right? So now they're asking us about the copper-2 ions when that is treated with concentrated HCl followed by concentrated ammonia. So again, they're setting us up for a ligand exchange reaction, right? So in my answer here, I wrote a series of ligand exchange reactions will take place, right? For the first reaction, we were adding to the solution of copper, we're adding concentrated HCl, right? So from the HCl, we're gonna get chloride ligands, and those are gonna replace the water ligands because this was in solution. So there were some water ligands there before. And then in that first case, we're gonna see a color change from blue, right, to yellow-green. So copper in water, when copper is complex with water, it's blue, right? And when the chloride then comes in and replaces those water ligands, we'll see yellow-green, right? And then in the second reaction, where we follow that up with concentrated ammonia, the ammonia ligands are then going to replace the chloride ligands that were there from this step. And so then we're going to see a color change from yellow-green, right, which is what it is when there was chloride there, to deep blue, which is when the ammonia has now substituted out all of the chloride ligands that existed before. So definitely make sure that you're comfortable with these equations if they were to ask you to write the equations that correlate or correspond to these changes, okay? So it's analogous to what we did for the cobalt, but in this case, we're talking about using copper ions and then putting that with HCl and then ammonia. So it's just a ligand exchange. Make sure you're comfortable with that and make sure you're comfortable with the concept of a stability constant, okay? So make sure you're good with that. And that's it, guys. This is more practice for transition elements. I hope you're starting to feel more comfortable with it. And as usual, let me know if you have any questions, drop a comment, let me know if this was good for you or just your overall feeling on it, okay? Thank you guys and see you in the next video.